Hello everyone. So today I want to continue the last lecture that I gave, but now speaking of a new duality. Instead of looking at the O(n) goes to 0 model, I'm going to look at the O(n) goes to infinity model. And this is really just a talk to inspire something called the spherical model, and to argue why it is a good model to study. So the basic references are the notes you can find in my GitHub page, which is Maestria Statistical Field Theory. It isn't uploaded yet, but I'll upload it this afternoon. The basic references are by Berlin, Kack, and Stanley. Berlin and Kack here were the first time that they studied the spherical model. And here's a reply to that model. It's saying that it's just the O(n) goes to infinity model. This is the Baxter's book is the one that I based myself for solving the spherical model. And as you will see, the spherical model, at least in the notes, is very rigorously developed. But on the other hand, the O(n) goes to infinity model isn't as rigorous. Now, everyone claims that there's this paper by Kack and Thompson that made a much more rigorous argument for the duality. I haven't found that paper. I don't know where it is. It's been so I'm just gonna go with the non-rigorous way to do it. I'm gonna do more of a plausibility argument and actually show that they're dual to each other. So, to begin with, the spherical model has a Hamiltonian which is the same Hamiltonian as the isomorph. All that we're going to change is the phase space of that Hamiltonian. So recall that for the IC model we have a Hamiltonian H from X into R, which takes every configuration of spins and assigns to it an energy minus J times the sum over all edges in some finite graph of SE1 times SE2, where E1 and E2 are the vertices of the edge, and this is the spin at edge at vertex E1, and this is the spin at vertex E2. That's the IC model, and all that we're going to change for the spherical model is change what X is. So we're going to take X as the sphere in n-1 dimensions, where this n is just the amount of the number of vertices in our graph. Okay? So that to be more explicit, what that means is the set of all functions which go from the vertices into the real numbers, such that the sum over all vertices of the spin at that vertex squared equals well, we're gonna take it equal to the number of points in the graph. And the reason for this is that essentially we want to think, it's better explained in the notes, but essentially one can think of the configurations of the IC model as the vertices of a hypercube, and that hypercube is circumscribed by precisely that sphere with that radius. So that's the idea. Okay? So instead of keeping motivating this model, I'm going to go right ahead and try to solve it. The motivation is, I'm going to say some words, but that's the first motivation, which is that the Hamiltonian is the same as the IC model, and the phase space is just, it contains the states of the IC model. In particular, the states of the IC model satisfy that equation. Okay? So the partition function of this model is given by an integral over all possible states of the exponential of minus beta h, right? So that's the exponential of beta j times the sum over all edges of SE1 times SE2. So that's the partition function of this model. Where here omega is just the measure in that sphere. It's just the area measure in that sphere. Now, here's a trick which is which we've used before, and it is kind of what led to the solution of the spherical model, which is to, instead of restraining the S's to be measure, we're going to allow the s's to vary over all the real numbers. And enforce the restriction through a delta function. So this is delta n minus this one. That's b squared. So that's kind of the trick that we're going to use, and this is another way of saying that the spherical model is useful, because that's the same integral that we had as in the Gaussian model, and that's the same integral that we had as in the Ising model. So in the Ising model, we have this delta, this direct delta. What it does is restricts each possible value to 1, right? In the Gaussian model, this direct delta function is replaced by a Gaussian distribution. And the whole idea of those distributions is that all of them, in some way or another, approximate the Ising distribution. For example, with this distribution, we have that the expectation value of each spin is 0. We have that the expectation value of each spin squared is 1, if we're in a homogenical lattice. We have the expectation value of this sum is n. And those are all properties that this measure has with the usual Ising measure. So, to solve this, now I'm going to take a very non-didactical approach, because the didactical way to do it would be to try to struggle with this and see what are the tricks needed, but I'm just going to do the tricks and they'll tell you why they were important to do in the first place. So the trick here is to add 0 to this exponential. And the way that I'll add 0 is by adding 8 times this restriction. There, I got it 0, right? Because by this restriction, this measure only has mass on the s's which satisfy this condition, and on the s's on which this is 0. Right? So all that I've done is add 0. And on the other hand, I'm going to replace this delta function by its integral representation. So I'm going to choose the integral representation of beta j divided by 2 pi integral dt of the exponential by beta j times n minus the sum times beta g of s squared. So that's the integral representation that I'm going to use. The reason why I put this extra beta j factor is because what I did when we scaled to what we usually do is because eventually this exponential is going to mix with this exponential, and these terms are going to these terms are gonna combine. So if I don't want any extra funny factors, I just have to put this extra beta j. So once I do this, I can see that my partition function becomes the partition function. It just takes it becomes Gaussian integration. Probably the same it becomes Gaussian integration. So that partition function equals the integral, or the product, p going to g of sp, and then I get an integral over dt. I get an overall factor of beta j divided by 2 pi. What's vg? Vg is the vertices of the graph. Is the set of all vertices of the graph. No. Here I have some graph. Just points p, q, r, s, and at each graph I have some spin, which is some real number. So it's just it's a vector, but it only points in the vertical direction, right? And the idea is that all those vectors, I can put them. Without those vectors, I can build a new vector, which is I take the first one and I draw it horizontally. I take the second one and I draw it vertically. I take the third one and I draw it in a third direction. I take the fourth one, I mean as many directions as vertices there are. Okay? And that makes up the space Rn, right? Which is the space of all vectors with with as many vertices as there are as components. I'm considering the sphere in this space. Okay? The sphere in this space. I'm considering the space as n minus 1. So for example, if n equals 2, so only PQ, then what do I, so this is SP and this is SQ. What do? I draw a Cartesian plane, and I draw SP here, I draw SQ here, and this is the point that I'm considering. Point SP, SQ, right? And I'm considering the sphere in this space. That's the meaning of the spherical model. Okay? It's not a sphere, it's not like in the ON model where we had a sphere at each point. Is that we have one single sphere for all the points. In particular, it is non-local, right? Because there is an interaction between arbitrarily far away spins. Because they must all add up to n, right? Okay. So of e, the exponential of now, if I take this term, and this term, I get n times beta j a plus I. So that's one exponential, and that's an exponential which does not depend on the configuration of spins, right? And on the other hand, I get another exponential, which is going to be of the form, now I take this term with this term, and that gives me a minus beta j a plus it. The sum over all p belonging to bj plus p squared plus beta j sum over all edges of SE1 times SE2. So this is familiar, right? This is this is a Gaussian integral. This is a Gaussian integral, and we already solved this integral in particular for the hypercubic lattice with periodic boundary conditions. We already solved it in lecture 2. But the problem is that I have to exchange these two integrations in order to make it a Gaussian integral. Now I can cop out and say that this is just because of Fubini's theorem, but I don't know enough functional analysis to state that, because this is definitely not a Lebesgue measure. What?
But you say this is not.
This is not a Lebesgue measure. This is not a Lebesgue integral. So I don't know what the real reason is, but if I exchange these integrations, this will in general not converge, right? Because this might not be positive definite. This quadratic form may not be, well, in this case, negative definite. So the claim is that I can indeed exchange these two integrations if A is big. So I can take A big enough to make that the real part of this is negative definite. That's the claim. And I don't know how to prove this in general, but when we restrict to the hypercubic lattice, then we actually know what the eigenvalues of these are. We calculated them in lecture 2. And we're going to see how we're actually going to get a bound for this to be true. But now proceeding courageously and just exchanging the limits, believing that we can if A is big enough, then we get beta j divided by 2 pi, the integral dt of the exponential of m beta j a plus it. And then we need to integrate this. But we already know what the answer to that is. That's the answer of the portation function to the spherical model. And that was done in lecture 2, so I'm not going to do it again. I'm just going to recall that the answer is pi n halves. So the answer to that integral is pi n halves. So that's the pi that appears on top of every Gaussian integration. right? And then I need the 1 over the square root of the determinant, right? That 1 over the square root, I'm gonna write it as the exponential of a logarithm of 1/2, of minus 1/2. So that's the 1 over the square root, right? And then I need to calculate the determinant of this quadratic form. But the determinant of that quadratic form is simply, well, it's going to be a product stuff, but under a product inside of a logarithm becomes a sum. And once when I go into the thermodynamic limit, that becomes an integral. So all of those were just to remind you that the answer of that integral is this. You can compare directly to what we did in lecture 2 to see this. Of u, which is what we had before, right? That u, but that u is right now beta ja plus it. Right? Minus the 2t, but 2t is now minus beta j, so beta j times the sum over I equals 1 up to d of the cosine of omega. And here I'm restricting my lattice to be a hypercubic lattice. So for example, I have a lattice of like 3, right? Which has these edges. And the boundary conditions are precisely that I connect this edge with this edge, 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 and these 2 edges. Those are the coordinates. So that's my lattice, right? So once I have that, are there any questions at this point? I'm going a little bit quick because there are a lot of things. I'm already like in page 8 of my notes. It's okay if there are questions. Okay. So now what we do is that we're gonna do a change of variables, okay? And we're gonna basically in here add d, and in here subtract d. And the reason for that is that the maximum that this can be is d, right? So I want to control when is this logarithm positive to understand the analyticity of this complex function. And to do that, I need to know when is the argument of the logarithm positive. The real part of the argument of the logarithm positive. So to do that, I do a change of variables, which is z equals a plus it plus d minus d. Oh, by the way, we already see what is the condition, right? Because this is at most d. These are the eigenvalues of my quadratic form. And because this is at most d, then the condition for this for the eigenvalues to have a positive real part is that a is bigger than d, right? That's the condition. So once I do that substitution, what I get is that the partition function at beta comma j equals beta j divided by 2 pi I. This I comes because dz equals I plus I times dt. Then I get a pi divided by beta j to the n half. So that's the pi of Gaussian integration, and this beta j is because it just multiplies all the eigenvalues, so it comes out of the determinant with an n halves. Of the integral dz from c minus I infinity to c plus I infinity, where this c equals a plus d, a minus d, sorry. Which is positive, because as we said, that was the condition for us to exchange integrations of n times of e to the n times phi of c, where phi of c. Well, first of all, phi is only defined on the upper half plane, on the rightmost half plane, so for positive real values. Which sends c into what we had over there, right? So that's b to j, so that's b to j times c plus d. This is this term, is beta j plus d, a plus lt. And then for the integral, we get minus 1/2 of the integral the omega divided by 2 d. The logarithm set plus d minus the sum equals 1 to d, the cosine of omega. So this is the partition function, and then yes, of course, we're going to want to go into the thermodynamic limit, so we're going to want to evaluate this by the method of steepest descent. So in the notes it is all rigorous on how to do this, but I'm just gonna talk to hopefully make it understandable what the point here is. So first of all, note that let us study this function phi for a bit. I'm not going to write anything down. Suppose that z is a real number. Let us restrict to real numbers. So when z goes to 0, this goes to 0, the logarithm blows up into minus infinity, but because of this minus, then the function goes to plus infinity, right? So that's a 0. At infinity, this blows up to infinity, this blows up to minus infinity, but this grows faster than this, so everything goes up to plus infinity, right? So we get that at 0 goes to infinity, at infinity goes to plus infinity, and the second derivative of this is going to be something of the form this, but 1 divided by this squared, right? So it's going to be positive. It's going to be positive always. So the conclusion is that there's a critical point in real line, right? On the other hand, when this goes when we fix the real part of z and we move in the imaginary plane, the real part of this function decreases. And the reason for that is that, well, the real part of this part doesn't depend on the imaginary part of c, so this doesn't care if we go up or down on the complex plane. But the logarithm, the real part of the logarithm, is going to be the logarithm of the absolute value of this number, right? And the absolute value of c is going to go to infinity as we move up or down. But we have a minus sign here, so this the real part of phi decreases. And moreover, this integral actually doesn't depend on c. And the way to see that is that if I'm doing some integration over, so say this is my complex plane, and I have some c1 and some c2, I want to do an integration over this. I want to compare it to the integration over this line. And we can extrapolate between both of them by doing rather an integration over here, then here, then here, then here. And this function is analytic because, well, as we already said, this is positive. The real part of this is positive. So this integral over this loop is going to give 0. But then, as we said, this function vanishes when I take it when I move up or down in the complex plane. So these two integrals, when I take them to infinity, they go to 0. So the conclusion is that the integral over c1 is the same as the integral over c2. So to conclude, there is a real solution to the critical value equation, which is the derivative of this equals 0. So there is a theta c, which is real and positive, which satisfies this equation. So that's the first conclusion, that there is a solution to this equation, and that it is a critical point, it is a saddle point for this, because it is also a maximum of the real part of phi in this conjugate integration. And in particular, I can choose c. C equal to zs. So I can make the integration go precisely through this critical point. So if I do that, then the partition function for the starting point method is simply beta j divided by 2 pi I times pi divided by beta j to the n halves. Then I get the primary contribution, which is going to be e to the n phi zeta s. And the quadratic contribution, just to write it down and make sure that everything we're saying is right, is square root of 2 pi divided by n times phi double rounded to 0. Which is of course well defined, as we already said this is possible. So this square root is real. Okay, so that's the partition function. Questions? No? So now we want to calculate the free energy in the thermodynamic. So the free energy we're going to calculate the free energy per vertex or per side. So that's the limit. It's minus the limit as it goes to infinity of 1 over n. Then logarithm of theta beta j. And this is easy to calculate. So this won't contribute because this doesn't depend on anything. So this would have a 1 over n factor in that, and it will go to 0. This contributes, and this contributes a minus 1/2 of the logarithm of pi divided by beta j, right? This term contributes because it's proportional to n under the logarithm, so that's minus 5z. And this term doesn't contribute because under the logarithm it goes like log n, right? But we have a 1 over n in front, and log n decreases. Log n divided by n goes to 0, as it goes to infinity by log. So this is the solution of this spherical model. So it is an exactly solvable model. Of course, the problem is then determining what zeta s is. That's a problem of computing the solutions to this equation. And that's it. Let me see how much time. So now let us go to the only one. The idea now is that we're gonna, actually the computations are pretty much the same. And we're gonna reach to the exact same free energy. So that's the duality between the spherical model and the O goes to infinity model. Or that's one of the manifestations of the duality. So recall that the O model, we had a graph full of vertices. And at each vertex, we have some spin, which is now allowed to be an n-dimensional vector. And each of those spins is restricted to be on a sphere. Okay? So that's the ON model. However, it still retains the same Hamiltonian that we've been speaking about. All that changes is that phase space. And thus, the partition function for this model equals the integral omega vg, where now we have one omega per one spherical measure per each side, so that's where I write the omega vg. Right? Of the exponential beta j times the sum over all all edges of SE1 times SE2 And we proceed in the exact same mirror image to what we did before. So we now express this as an unconstrained integral. Where now at each point we have a vector spin. And we enforce the spherical condition by a product of delta functions. So for each point we have the restriction that this is satisfied. So that's the partition function. Now, doing this restriction has a very nice property, which is that actually dimensions decouple from each other. So in the spherical model, the first time that I treated it, we had this problem that because this is a dot product, then dimensions are highly coupled, right? Because they all have to do with have to add up to a sphere, right? All the dimensions have to make sure that their components add up to a sphere. Once we restrict the integration, then the dimensions decouple because the dimensions can be whatever they want, right? So I can replace that dot product by sum. I can replace that dot product by product here over all dimensions. And here take this 1i, this e2i. So in that way, the dimensions are now decoupled, right? Which didn't happen before if we didn't unrestrict this integration. So now the idea is that I'm going to do exactly the same. So I'm going to introduce a factor in order to change the integrations, the order of integration, and that factor is simply going to be
now it's delta function. You will do the same thing per delta function, right? For each delta function, you will use an integral representation, put some factor, shape, blah blah.
Yeah.
I don't take it into the
okay.
final result.
Yeah. Okay. So
is it clear for everyone, right? It's just the same thing. It's just now we have many delta functions, so we'll have many integrations.
I mean, there's clearly going to be a complication with respect to the first case, which is that each of these delta functions will now have a coefficient that t is now going to depend on every point, right? So the quadratic form that is going to pop up is not homogeneous.
Yes.
So it's not solvable by the Gaussian solution. We cannot use the Gaussian solution that we used before. We can still use Gaussian integration, but we don't know the eigenvalues of the quadratic form. Okay. So, but I can go to there. I mean, it's clear that it's the exact same solution, except that before I could write explicitly what the determinant of the quadratic form was. Now I just have to leave it expressed out. So I'm gonna go up to there. So by doing that, we get exactly the same integral as before. So we get now theta beta comma j equals beta j divided by 2 pi I. So the same expression that we had, the same coefficient that we had before, divided by beta j. But now before, what was the number of vertices is now the number of dimensions in the model in half. And this all is powered to the number of vertices, okay? And I get an integral over all of those uplines, right? With one per each point in the vertex. Of the exponential of n times phi of z. Where now phi of z is exactly what we had before, because of that thing that I just mentioned, that we cannot calculate the determinant explicitly. But that phi of z is going to be similar. sense that phi of z is going to be equal to 1 over n times beta j times the sum over p belonging to bg of c and p plus d minus 1 half of the logarithm of the determinant, right? Where now this determinant is given by, that's the determinant of the following quadratic form. That's the determinant of the quadratic form. So symbolically we could write the determinant of the quadratic sum from sum p belonging to bg of b plus itp plus p squared minus the sum of wedges SE1 plus SE2. So this is what I was telling you about this TP. So we don't have uniform coefficients, so we cannot precisely use the previous solution. So this is precisely because of this problem, this inhomogeneity of the TP. This is where Stanley's article becomes a little bit possibility argument rather than proof. But the statement is that now what we're going to do is consider that a critical point where that C is homogeneous. Okay? So at the level of, when we're doing everything generally, we couldn't ask for C to be homogeneous. But when we look for this output, he argues, but I don't understand that argument, that at the point of using the saddle point method, one can take all the C's to be homogeneous and then go back to this to our Gaussian solution. Once again, I wasn't for the argument he goes to another paper. I didn't see an argument in that paper, and then everyone says that the rigorous duality is in another paper, which I haven't been able to find. It's kind of lost. But let us for the moment suppose that this set is indeed homogeneous. So that we now have, once again, that the critical point is given by this equation.
You are doing saddle point approximation using little n now as your
No, using
parameter.
both. I'm going to take both to infinity, so I'm using the product. Yeah.
Okay.
So this big N goes to infinity because we want to go to the thermodynamic limit.
But the phi of z has 1 over n overall. So that's why.
No. But this term is going to go when set is homogeneous. Because when set is homogeneous, then this sum gives an extra n term, so that cancels this, and the determinant is going to get an extra n. So if you remember, this is going to be the logarithm of n, the exponential of the logarithm.
N integral.
Yeah. So there's going to be an extra n, which is going to cancel that 1 over n. Yeah. Okay. Good catch. So. And this is precisely the same saddle point that we got in the spherical approximation, and then, well, this partition function goes into this integral.
I think you don't have to continue. If it's the same saddle point, it's always the same result. But can you try to argue why it is homogeneous?
No, I can't. I'm not going to try to.
Because it's only interesting thing. Everything else is trivial once you say that I'm going to use a delta function to write an integral. No? Well,
For me, it wasn't trivial.
No, but once you say delta function is going to be an integral.
Yeah.
I have many integrals or one integral. If it's homogeneous, it's the same thing. No difference, right?
Yeah.
So I think the only deep statement about the duality is showing that this saddle point, the solutions are independent. Otherwise, why do we need to spend more than 3 seconds looking starting point and saying I have one delta, I have many deltas. If I assume that later the saddle point is going to be the same, the models are dual. Why would I write the paper? Right? Just say it in 3 seconds.
I mean, okay, so let me attack each of the points that you just said. So let me regard each of the points that you said. So first of all, for the homogeneity of Z, I don't have an answer. So he claims that this is the point where the paper is not rigorous. This is the point where yeah, as you said, it becomes an observation. So that's why nobody claims that Stanley was the first one to prove this duality, but everybody claims that Stanley was the first one to observe the duality. I don't know why this should be homogeneous. He claims that some people did it for the Ising model and that it extends, but I read the Ising model paper and I don't see any argument for the homogeneity of the set. And once again, the paper that's supposed to make all of this rigorous, I couldn't find it. Regarding the trivialness, indeed, the O(n) goes to infinity model is trivially like the spherical model once we assume homogeneity, because it essentially becomes a product of the same partition function, right? Of the same partition function of the spherical model. So I guess the non-trivial part of this lecture was actually understanding what the spherical model was. So the solution to the partition function of the spherical model.
Okay, but then can I ask you, what's the physics of the spherical model? Where does it appear?
Okay, so the spherical model, so there are 3 justifications that I understand for the spherical model. The first is, as I said, and I'm going to extend on what I said before. So the first is that the phase space for the Ising model is just -1, 1 to the end, right? So that's the vertices of a cube, which is -1, 1 to the end, right? So for example, in n equals 2, the phase space of the Ising model is just this vertices. This vertices of this cube, where this axis is SP, this axis is SQ, and equals 2 means that the graph only has 2 points. The spherical model, the original motivation for the spherical model was trying to find an exactly solvable model whose phase space contained the phase space of the Ising model. Okay? And what they reached to was, instead of considering the vertices of the square, consider a sphere which circumscribes that hypercube. So that's the first motivation, just trying to find a system which is the same Hamiltonian, but modify the phase space in order to get an exactly solvable system. Of course, this doesn't say anything about that it is actually a good approximation, right? And moreover, it makes it kind of have like an physical feeling, because this model is non-local. All of the spins interact with each other in order to make that all the spins form one sphere. The second motivation is what I said about the comparing the Gaussian, the Ising, and the spherical models. By the Gaussian model has a Gaussian probability distribution, the spherical model has a spherical probability distribution, and the Ising model has a product of discrete probability distributions. I'm comparing those 3 distributions, right? And seeing that they have similar averages and they have similar properties. And the third, which is the one that made people believe in the spherical model in some way, is that duality, right? So the spherical model physically coincides with a physically very sensible model, which is the O(n) model, right? Which is an extremely sensible model. It's a model where every spin has its magnitude constraint, but that's it. Right? And that's the limit as the dimensions go to infinity. So that's a reason. So if you recall, the O(n) model for n equals 1 is the Ising model, for n equals 2 is the xy model, for an impulse series, the Heisenberg model. So people think that the spherical model is an approximation not to the Eisen model, but rather to the Heisenberg model because 3 is bigger than 1, and 3 is closer to infinity than 1. So those are the 3 motivations.
But you can not construct it in a lab, for instance. The people do not use this in condensed matter.
I don't know. There are some experiments which if there is some system which has the critical properties of this, I don't know.
I think it should be hard to do it because of the property of non-locality.
Yeah, but this is telling you that you will get the same, you will be in the same universality class if you instead of thinking of it as a non-local interaction, you think of it as spins which are arbitrarily high degrees of freedom.
So is mean field exact for this model?
For the spherical model.
Well, they are the same as it shows, isn't it? Okay, for the spherical.
Let me write down the partition functions to see if we see how to do mean field there. Just circle the partition function. So this is the partition function. So doing field would mean that let us replace. So let us imagine that this is one field that this is interacting with. And it will be on the less b to the minus b to j. All points b belonging to bj. Sp times the magnetization times d times the magnetization, right? Where d 2d times the magnetization. So that would be doing mean field theory, right?
You are doing which model? The spherical model?
Yeah, the spherical model. And in mean field theory there, we have a problem, which is that no, mean field theory definitely cannot be exact, because then you have the problem that the expectation value of SP of the sum of the SP squares is equal to n. It is the spherical.
Why do you do that?
I mean, this is a property that the spherical model has.
Yes.
Yes, and this is not true for this. Right? Because if I try to calculate this.
Oh, but that condition is still in the measure, right? Why would you?
No, yeah, you're right.
When you write in non-constrained fields, this condition would be there.
Yeah, it's the right condition. SP equals to 0. SP squared should be equal to 1. Yeah, it has the same properties. I have the intuition that mean field should be exact, right? Then the solution should be trivial and the solution was highly arbitrary.
I think the question is that if the constraint changes the mean field of mean exact to non-exact. So if you start without the constraint, you have a mean field exact, and then you put a constraint and see if it's still exact or not.
No, I don't think that's the question. Mean field was not exact to start with. Why was it exact?
Okay.
He's saying that exactly if we
Right,
replace this
model,
one.
right. here we have n is very large, you have many components, and it looks more like a Siano's model where everyone is interacting with everyone. Here, not everyone interacts with everyone, it's just neighboring edges. But because of this non-local constraint, you are kind of introducing an everyone with everyone interaction.
Yeah, that's true. That's true.
So the question is whether the main field becomes exact.
I don't know. Yeah, that's a good point, right?
Let's see from the spherical model point of view. Yeah, from the spherical model point of view, it's less obvious because there it's just neighbor. But each of them is a very big free space. There it's less obvious. Here it smells like Minfield because of this non-local interaction. It looks more, but
I don't know. We try to solve it. So if I unrestrain the integration, so this is now the integral that we need to solve. And now this integral has something very nice, which is that this integral breaks out into that exponential, just like in the Owen model, the exponential, the dimensions decoupled in the mean field theory of the spherical model, the vertices decoupled. So to see this, the delta function equals some integral dt of e to the it of n minus this sum, so I can write it as etn times the product of exponentials to the minus it sp squared, right? So at the end, what I get is, if I switch out the integrations without thinking about it, I would get 1 over 2 pi. That's the integral dt of eitn. Again, this is again, sorry. And then I would get the integral ds of e to the minus its squared minus 2d e to j sm. All this here. Now, that's a Gaussian integration.
yeah, but it's always not going to be the same. You're never going to get these cosines. It's different. It's a different. It's not the same. Infield, right? The cosines are gone now. You're never getting them back or anything similar. So it's probably it cannot be just infield. This is too simple, right? Yeah. Okay. Good. Yeah. So it's interesting. So this large M model is dual to another model. Yeah, it would be nice if the other model had some physics, right? Otherwise, yeah.
I mean, the physical, I didn't have time to study this, but what people claim is that the physical interest behind this is that it was shown that certain critical properties are monotonic functions of the parameters in the O equals infinity model. So that made the spherical model approximation to the ISO model have that same critical behavior, but I didn't study that.
Yeah. No, the rest is tyrannical, yeah, spherical model. Yeah, it's only, there's no parameter there, yeah.
And in GitHub you can find all the details. I really struggle to understand. There is some very nice complex analysis